Okay, good morning, everybody. Welcome to day 3 of Secure Computation. A shout out for the karaoke last night. Lots of good times. And in addition, we had 70 people sign up for the senior junior lunches, so I'm very excited about that. We've done the pairing. Huge thanks to Lisa Cole and Divya Ravi.
So one-on-one?
No, it's going to be groups.
You said pairing.
Okay. Pairings in a non-monogamous sort of way. So yes, groups is what it's going to be. So hopefully during the break, we'll have some printouts. Take up. You can see on the sheet who else is in your group, as well as what day you're set for. So it's either today, tomorrow, or Friday, and there's different groups. And there'll be more information about that. Excellent. So without further ado,
Why are you holding the microphone?
It's supposed to be on. I'm used to the karaoke. I'm already. This is why. Good. Okay. So over to the technical part of today. We'll be starting out with a couple talks about private information retrieval, beginning with Henry Corrigan-Gibbs, who will be celebrating the 30th birthday of PIR.
Great. Thanks so much for the invitation, and thanks everyone for showing up early in the morning. So when I was preparing this talk, I realized that it's the 30th anniversary of the original private information retrieval paper. And so I looked on the internet for information about what happens when you turn 30. And I found lots of good things happen. And I was thinking, actually, for private information retrieval, these have also happened. We have better bounds, upper and lower. We maybe don't care as much as we used to about assumptions or crazy models. Communication has improved exponentially. Not perfect, but still pretty good. And maybe we're less self-involved and care more about applications. So I think there's many good things to expect in our 30s. So the goals for this talk are a few. I wanted to give kind of a survey of PIR, a very brief and incomplete survey, but to give you some kind of structure to think about the literature, because there's a lot of schemes out there now. And for people who don't work in the area, it's sometimes a little intimidating. The other is to share some of my favorite ideas in PIR that I hope have applications to other MPC protocols and systems. I think many of the PIR ideas have not escaped yet, and I hope that they do. And then I'll mention some open problems. So I asked a few people for their favorite PIR-related open questions, and I've included them in the talk. And I'm just going to warn you that I'll be pretty informal, so I'll be suppressing log factors and constants all over the place, but ask me if anything seems unclear. So good. So what is private information retrieval? And I realize there's a typo on this. It should already say Goldreich. Sorry. The CGKS paper from 1995. Should I fix this now? Yeah.
I think that this is too late.
Yeah, the internet already knows. OK. So good. So the idea is to read a bit from a database without revealing what you read. So the database we're going to think of as an n-bit string. The client interacts with 1, 2, or more replicas of the database. And we're going to try to get security, at least for the purposes of this talk, against one malicious server. So even if there's k servers, we're just going to get security against one. And so we have a few kind of normal properties we ask of a private information retrieval scheme. The first is correctness, which is just if everybody does the right thing, the client gets the right answer. And you can generalize this in many ways. But for the purposes of this talk, again, we'll stick with the simple one. Then client privacy is kind of a semantic security notion where we want to say that the server's view, malicious server's view, should look the same whether the client's looking for index I or index j. And we can ask, as usual, for statistical closeness or computational indistinguishability, depending on what we're trying to get. And then the traditional goal for PIR is that we want to minimize the communication between the client and the servers. So that's kind of the basic setup. And the reason I got excited about PIR, and I'm still excited about PIR, is that it seems like if you could build practical PIR systems, you could build all sorts of interesting applications on top of them, like private web search or even private web browsing, private messaging, private video streaming. All sorts of things could be possible if we could build big-scale PIR systems. But 30 years into this, it's sometimes not clear if we're any closer to this vision than we were at the beginning. So I'm hoping that by the end of the talk, this kind of mess of PIR schemes has a little bit more structure in your mind. So this is what I hope you think the literature looks like. So good. The first part of the talk, I want to just mention kind of the motivating question for PIR. What how much communication it takes to read a bit privately from a database. And I'll mention kind of the view that I kind of have adopted, and one trick that I think is pretty cool. And then in the rest of the talk, I'll focus on computation, which is really the practical barrier, is reducing the server work. And at the end, I'll mention a couple of applications. So good. So I think one way to think about private information retrieval, which I think is a very useful way, and this is very much influenced by this paper of Bimal and Ishai from 2001, is thinking of it as private polynomial evaluation. So instead of thinking of the servers as having a database, think of the servers as having a polynomial, a multivariate polynomial. And the client has a secret evaluation point. And after this interaction, the client should know the value of this database polynomial at its secret point, and the server should learn nothing. So this is sufficient for private information retrieval in the following sense. If your polynomial has like enough coefficients, you can actually find some n fixed interpolation points, I'll call them q1 up to qn, that are independent of the database. So these just depend on the size of the database. And then the server can just interpolate a polynomial through these points. And if your polynomial has enough coefficients, you can just use standard multivariate interpolation to do this. And then any protocol you have for private polynomial evaluation gives you a private information retrieval protocol. So that's, I think, one way to think about many of these constructions.
Why do you insist on polynomials?
I don't insist, but I prefer. I think it's just a nice way to think about it. It's not.
You can generalize it to homomorphic secret-sharing of a function class with a high VC dimension, where the VC dimension of the class is lower bounded by the database size. This is the most general abstraction of this.
Yeah, I don't think this is necessarily the be-all and end-all, but I think it's useful. So if we take that view, then, as I mentioned, the polynomial has to have kind of enough degrees of freedom, enough coefficients. And what it turns out is that you have an m-varied polynomial with the total degree d. You need the number of variables to be like n to the 1 over d. So as the degree goes up, the number of variables you need goes down. So once you have that view, it's actually pretty direct how you get PIR schemes, at least single server and multi-server both. So what you can do is if you have a homomorphic encryption scheme that supports evaluating degree d polynomials on encrypted data, you can use that to make a PIR scheme as follows. Basically, the client has its point that represents kind of what it wants the kind of output of this polynomial evaluation problem to be. The client just encrypts that point with a homomorphic encryption scheme, sends it to the server. The server homomorphically evaluates the polynomial on that point and sends the answer back to the client, and the client decrypts. So if you have a homomorphic encryption scheme for degree 1 even functions, then you can get a single server PIR scheme. And essentially all of the practical PIR constructions that people use in the single server setting follow this recipe, more or less. There's lots of optimizations and other things you can do, but this is the basic picture. And then this is sort of relating to what you've all just said. In the multi-server setting, the analog is, instead of homomorphic encryption, it's homomorphic secret sharing. So these are secret sharing schemes that let you apply degree d functions to secret shared data. And very much in the same way, the client just sends secret sharing of its points up to the servers. The servers apply the database polynomial homomorphically and send the answer back to the clients. So what you can see if you stare at this for a minute is the communication cost, say in the single server setting. The upload is the encryption of a m-variate element. And the download is just the encryption of one element, say if you're working over a field. And so the communication cost is roughly n to the 1 over d, ignoring all the low order stuff. So what this means is that the more homomorphism you have, the more powerful an encryption scheme you have, the less communication it's going to cost you to do PIR. And once you get to like logarithmically log degree polynomials, you can get the communication very small. And after a little rebalancing of the upload and the download, you can actually get communication like n to the 1 over d plus 1. So communication-wise, that's what the picture looks like. Computation-wise, applying this polynomial is going to take time linear in the database size if you do it the normal way. Any questions about this so far? Okay. Are people awake? I see someone. Yeah.
So how does it scale if I want security against 2 servers?
Yeah. Well, so in the single server setting, you already get security against.
Right.
Yeah. In the multi-server setting. So I'll maybe say one thing about that, but we don't actually know. We don't know the answer to this question. And
can you repeat the question?
So if you want privacy against two malicious, say you have a 3-server scheme and you want privacy against 2 malicious servers colluding, what is the communication, how does the scaling look like in that setting? I'll mention that. That's one of the open questions, actually, that you all
The issue is really with the homomorphic secret sharing component.
Yeah, that we don't have as nice a characterization of when homomorphic secret sharing, what's, yeah, of the
There should be
landscape.
some naive reduction that gives you something, right, from the single. Maybe not.
You can.
Not totally clear. Yeah, maybe we'll come back to it. All right, so in the multi-server setting, just to give you one example instantiation, so for Shamir secret sharing, say if you want to have 4 parties with 1 corrupt, you can compute degree 3 polynomials on Shamir shared data. And so what this gives you before you do the rebalancing is like a 4-server PIR scheme with, that tolerates 1 corruption with communication costs like cube root of n. So I'll sketch the scheme just because I'm going to show you one extension to it in a second. But the way it looks is the client just generates a Shamir sharing of its evaluation point, sends 1 share to each server. And this is the database polynomial here is like a polynomial with cube root of n variables of total degree 3. And the servers just apply locally this database polynomial to their shares and send the answer back to the client. And now this polynomial p of x I've written here is a degree 3 polynomial. And the client has 4 points on it. So it can just interpolate to recover this polynomial, evaluate it at 0, and that gives it its sort of the point that it was after, the evaluation point it was after. So that's PIR from Shamir secret sharing. So if we look at this, what the cost looks like for 2 servers and k servers with this basic Shamir scheme, it's like n to the 1 over k is the communication cost. There's one trick that I'll mention that improves the communication cost by a little bit. So it's like n to the 1 over 2k. And I think this derivatives trick I think is a cool one that people should know. So I'm gonna explain it to you. What I'm not going to explain to you is the best known 2-server PIR scheme, which has communication sub polynomial in n. So it's like 2 to the square root of log n. And that is an extremely clever construction that would take way too much time to describe. But I have a pointer to the place you should read to learn about it if you want. The other thing that you may notice if you've seen locally decodable codes is that there's a very close connection between k-server PIR schemes and k-query locally decodable codes. And so the techniques we use to construct these information theoretic PIR schemes are exactly the same techniques used to construct locally decodable codes. So this first construction I just mentioned is very much like a Reed-Muller code. The derivatives technique I'll show is like a multiplicity code. And these state-of-the-art PIR schemes use ideas from matching vector codes or vice versa. Cool. So yeah, so I want to show you this one derivatives trick. Actually, how many people have seen multiplicity codes in this audience? OK, good. So almost no one. So I hope this is, how many people have seen Shamir secret sharing? OK, good. All right, so now I hope we can bring these 2 crowds of people together. Yeah, so I want to show you this trick, which I think is a very cool one. So again, what we're going to do is reduce the number of servers. One way to think about it is you cut the communication from n to the 1 over k to n to the 1 over 2k. A different way to see it is you cut the number of servers in half, the number of servers you need to achieve a particular amount of communication. And again, I think this should have more applications, so I hope that you can come up with some. So the basic idea is a simple observation that if you're going to interpolate a degree 3 polynomial, you need 4 points. This is kind of high school, maybe even middle school. But it turns out you actually only need 2 points. You only need 2 points on the polynomial if you also have the evaluation of the derivative of that polynomial at 2 points. Yep?
This is Hermite interpolation.
Yeah. I had it on the slides at one point. But yeah, this is, I think the citation here is more about the application than the.
You also sometimes do not need points. You can have infinities, and if you go to homogenize it, you don't need the concrete points.
Yeah, absolutely. And on the left, I should also be, maybe it should be Lagrange reconstruction. Depends on, yeah. Lagrange is not in the audience, so I'm not worried about it.
Just need Gaussian elimination, right?
Say again? The Greeks are, what?
You need only Lagrange to say that there exists an interpolating polynomial. You can use Gaussian elimination to interpolate.
Absolutely, yeah.
Lagrange is only there to say that there exists a solution.
Yes, yes. I hope Gauss is not. No, I knew. OK, we can get this behind us now. I already messed up at least 2 citations. So I hope I don't have too many more. So, anyways, this idea I think is super nice, and it has a very nice application to PIR, or I guess same locally decodable code. So the idea is the client's going to send Shamir secret sharing to the servers. It's going to send to points on a line. And now, instead of having 4 servers reply, we actually only need 2 servers to reply. And they'll reply with the evaluation, like evaluating this database polynomial on these points that the client sent. But they'll also evaluate the gradient of the database polynomial on these points that the client sent. And from this information, the client has enough information to reconstruct this database polynomial on its chosen point. But we only needed 2 servers instead of 4. And the catch here is that now instead of sending kind of 1 field element back, the server is going to send, the gradient takes like cube root of n bits to represent, or cube root of n elements to represent. But we cut the number of servers in half. So an equivalent way to look at this, which was, I think, the first time I saw this was in a paper by Ishai, Lai, and Malavolta, is this is like a 2-party homomorphic secret sharing scheme for degree 3 polynomials with share size like cube root of n. Good. Yeah. So good. Yeah. So with higher order derivatives, you kind of keep blowing up the download and shrinking the upload. And if you take this to the limit, you get, say, a 2-server PIR scheme with order like log n bits of upload and polynomial download. So it's not obvious why you would want this, but I'll come back to this in a second. Does that make sense?
It doesn't prove the 2-server. Doesn't you prove the 2-server?
No. No, it doesn't meet, so the matching vector stuff is all sub-polynomial total communication. But if you want a PIR scheme with extremely small upload, which I'll explain in a second why you might want that, then this is the way to do it. Yeah.
So what is the asymptotics for so as a function of the number of derivatives, also for the server storage might also be an issue?
There's no storage issue. So this you can compute these things all online. Yeah. What's the asymptotics for these things? I think once you get, I don't have like a clean expression in my head, but yeah, good. OK, so this is kind of the landscape, or at least a few points in the landscape of the communication cost of PIR. So this derivatives trick gets you another factor of 2 in the exponent. The matching vector stuff is a huge improvement over that. The sort of puzzling thing is we don't have very good lower bounds for PIR. So the best lower bound, I think, is 5 log n bits of communication, where log n bits.
Both directions sum or
total communication, yeah.
Total?
Up and down, yeah. Yeah, so like very, very weak lower bounds. In the computational setting, we have a much better story. So I'm not going to give this construction. This is Boyle, Gilboa, and Ishai. It's really Gilboa this time. With like log n bits, if you think about a PRGC as being lambda bits long. And then from many different public key assumptions, we get single server PIR with like polylog n communication. But this gap is gigantic and has been open since the first paper. What I wanted to mention is that if you want to learn about this PIR scheme, which is super, super interesting, there's a really nice paper that came on ePrint last year that has, I think, good intuition for how that construction works. I guess the other thing I should point out is that in practice, we are typically fine with assuming one-way functions exist. And in that case, these schemes are extremely communication efficient. So even for extremely large databases, some kilobytes of communication is all that's needed to do PIR. So good. So in terms of PIR communication, here are some of the open questions people mentioned to me. So Niv asked, is it possible to get constant server information theoretic PIR with polylog n communication for any constant number of servers? And that seems like a very difficult question. It has been open for a long time. But yeah, we still don't know, say for 5-server, 10-server PIR. Yuval mentioned this one that relates to Benny's question earlier. Is there a 3-server, 2-private PIR from one-way functions with sub-polynomial communication? So for 2-server, 1-private, we know that it's like log n, or lambda log n, something like this. But if you ask for 2 privacy, I think the best construction is square root. Is that?
With 3 servers,
yes. Yeah.
With 4 servers, you can already get into the little.
Yep.
Information theoretically.
Right.
So the server to private might be possible even information theoretically.
Yeah. Yeah. So this is to make the question easier for you, but still hard. Yeah. So you can remove the from one-way function.
This would have the application, PSM and things like this. Is it cool? For private simultaneous.
Yeah. I'm the wrong person to ask about that.
Yes.
Good. Okay. Yeah, and then you could ask, like, is there a two-server PIR scheme that beats this sort of lambda log n? You could ask for, like, lambda plus log n. That also seems hard, but no reason to be impossible. And Vinod sent me this question, which I thought was sort of, hadn't thought about before. So if you have a rate 1 OT scheme, you get a homomorphic encryption scheme for branching programs, certain kind of branching programs. And Vinod asked, is there like a similar thing boosting single server PIR to fully homomorphic encryption? So is there some property, like a simple property, that if your single server PIR scheme has that property, then you can actually construct an FHE scheme from it? And yeah, I have no idea what the answer to that would be, but I thought it was a nice thing to include. Good. So I think the takeaways from the communication part are that I think private polynomial evaluation is one convenient way to think about many of these schemes. The computational cost in practice is extremely low. In theory, we don't know exactly the right answer for these information theoretic schemes yet. But it's not, I wouldn't say this is the barrier to using PIR schemes in practice. The communication cost is already good enough. Good. Cool. OK, so I wanted to talk about computation, which is, I think, one of the big things that prevents us from using private information retrieval in practice. Yeah?
Maybe one question. So in the practical world, like how do people treat this assumption that the servers do not collude? Like is it something that people believe or I don't know?
Yeah, so the question is like, how do people feel about non-collusion assumptions in practice? So my sense is that if you can do something exciting while making a non-collusion assumption, people are fine with it. Like if it's an interesting enough result that you get, people are OK with a strong enough assumption.
You're talking about accepting the paper or selling the system?
No, actually in practice. It's like if you tell a company, like, look, I'm going to make you billions of dollars, but you have to assume there's two non-colluding servers. They'll find a way to make it work. I also think, I mean, maybe a less glib answer is, I think there's many settings in which we already make non-collusion assumptions in practical systems. So for example, in the DNS ecosystem, when they have these like key signing ceremonies. They have 8 shares of the key. Everyone comes to a room. But really, security is premised on one person not getting all the keys. And I think people are very happy with that kind of setup.
But when you have 3 entities or 2 entities?
I mean, they have 8. It's even worse, right? So it's even more coordination. So I think if the resulting system's interesting enough, people are willing to work a little bit.
DNS, they also only do that every 4 months.
True. But another example would be, say, Apple uses this for their private relay system. They pay Fastly to run an infrastructure. And if Fastly and Apple collude, the privacy is gone. But I think Apple's sort of OK with pitching that as their setup. Good. All right. Cool. So I'll spend most of the rest of the time talking about the bad news, which is that, well, the good news that comes after the bad news. So this comes from, this is Bimile, Shai, and Malkin in 2000. This lower bound that says that if a PIR scheme is correct and secure, even computationally secure, and stores the database in unmodified form, then to answer a single PIR query, the servers have to run in time linear in the database size. So servers have to touch every bit of the database in responding to a query. And this lower bound is strong in that it holds even against K-server PIR schemes. You make strong non-collusion assumptions, make whatever computational assumptions you want, and you don't restrict the communication between the clients and the servers. That's pretty robust. And the intuition, if you haven't seen it before, is that if the servers don't touch some bit of the database while answering your query, then the client kind of couldn't have possibly been reading that bit of the database. So you end up with a privacy problem. I think Mohammed's going to talk about this in like half an hour. This extremely neat strengthening of this result that says in the single server setting, the server not only has to do linear work, but has to do linear public key operations for some definition of what a public key operation is. So that's even worse news. So I think the picture I have is like, oh no, we can't get to any of these beautiful things because the communication cost is just too high. For kind of any interesting application of PIR, the database is really huge, and it's not clear that we'll be able to scale to handle those things. So as usual, as soon as you get a result like this, you try to subvert it in all the ways you possibly can. So you can relax the correctness guarantee, you can relax the security guarantee, you can encode the database, or you can answer many queries with one linear scan over the database. And all of these relaxations give you different ways to get sublinear time PIR, kind of get around this result. Yeah?
Last one, you mean that like when we see a single client query, the load bound doesn't hold if like a non-adaptive set of queries, you would need more than.
Right. It doesn't say that to answer 2 queries, you need 2 unwork. It just says to answer 1 query, you need 1 unwork. Yeah. Cool. So I'm not going to talk about relaxing security, although people do. I will talk about these other 3 approaches and what people have been working on, what kind of where the state of the art is with those things. The first one I wanted to mention is maybe the most, I think the least powerful of these, but also something that we thought was kind of interesting. So this is actually joint work with my students Ryan Lemkel and Alexandra Hensinger. And our kind of observation was that often in many real-world databases, some database records are much more popular than others. So the headline articles maybe are read much more often than the articles at the back of the newspaper. And if you have a database like this, maybe standard PIR correctness, which is kind of a worst-case correctness notion, is overkill. You know, PIR correctness is saying no matter what the client's looking for, it's definitely going to get the right answer. But instead, you could say something like, well, if the client's query follows some popularity distribution that we expect, then the client's going to get the right answer. And if the client deviates from this distribution too much, then maybe it'll get the wrong answer or won't get any answer.
Do you know when you get the right answer?
The client does know, yeah. Yeah. But it still has to deal with that somehow. And it turns out, I'm not going to go into this, but you can get sublinear time PIR with standard PIR security in this setting. The limitation being that your application has to be able to tolerate this relaxed notion of correctness. So in the paper, we go into applications where that does come up. Many it doesn't. Yeah?
Why can I do just lossy compression and then I understand that this thing?
Lossy compression on the database? Yeah, there's
no way the list.
Exactly, yeah. You can do this kind of stuff.
So it's not about pair, it's about compression. Then use your favorite pair, like from the previous slide.
Sorry. I'm not sure what you mean. Maybe it depends on where you draw the boundary of what a compression scheme is and what a PIR scheme is, but there could be some other way to do it for sure. Yeah. I think just the idea or the thing that I wanted to point out is that relaxing correctness is not necessarily ridiculous in all applications. And that is one way to get around the PIR lower bound.
Even if the distribution is uniform, it works. There's no condition on the distribution.
No. Yeah. Good. So this is can, so not always. I should say this depends on how skewed your distribution is. So in some sense, the uniform distribution is the worst case for this. If your distribution is very heavily skewed, then you get better and better speedups. Cool. Yeah?
There's something kind of strange where the people who are on the tail of the distribution are the people who kind of need privacy the most potentially because they're doing something that's most out of the norm. And so you're not compromising privacy for those people, but in order for them to correctly get their thing, they kind of have to go somewhere else, which is not private. So there's a weird trade-off happening there.
Yeah. So I don't want to get too deep into this, but I think the applications that we were looking at are ones where it's not that you'll never be able to get what you want, it's that you'll wait longer to get what you want. So you won't get your article as quickly, but you'll eventually get it. But yeah, I think it's better if you don't have to worry about these things, but I think just as kind of exploring the space of solutions, I think that's one thing to keep in mind that you can do.
You will eventually get it by doing more actions?
Imagine,
That would violate.
No, I think the idea is, or the applications that we're looking at are ones in which your computer is making queries every second or every hour, some background job. And if you happen to be on the good part of the distribution, you'll get the answer more quickly. If you don't, you won't. But you definitely don't want to reveal the bit of information of whether you got the right answer or not, because that, of course, depends on your index. So you have to be careful. But
Is there a side channel here?
I think the answer to this question is always yes in the crypto system. But at least not an obvious
Not if you're
one.
patient.
Not if you're patient, yeah. So
Oh, but how do you know that you got the right answer?
So the PIR scheme, so we have a more complicated notion of correctness that basically you learn whether you got the right answer or you got nothing. So the PIR scheme gives you either a bit or it gives you bottom. And so, yeah. So that you have to worry about many of these things, but I think if you're interested, you should check out the paper. OK, so the second approach, I think, is a much more plausible one in general, which is to reuse one linear scan to answer many client queries in one go. And there's kind of two techniques I want to talk about here. The first is batch PIR, which is sort of addressing Muthu's question, which is there's a non-adaptive batch of queries, either from the same client or from many different clients, and you'll use one linear scan to answer them all. The other approach is a client is going to sort of set up a session with a server, which is going to require linear time for the server. But thereafter, the server can answer each individual client query in time sublinear in the database size. So the first one I'll mention, this is from this IKOS paper, 2004. To answer naively a batch of queries, like k queries is going to take n times k cost. What they show is that if you have k queries from the same client, the client can kind of set things up in such a way that answering all k queries at once just takes essentially linear time. And again, I'm being very sort of smushy with the low order terms here. The basic idea is you have the client and the server. One way to do this is you have the client and the server kind of virtually split up the database into random chunks. And then likely, most of the queries the client will only need to make one query to each chunk to get all of the answers that it wants. And so you have k chunks. Each chunk has size n over k. The total computation on the server is roughly n. And there's many practical improvements to this. This does give you real speedups whenever you want. One client wants to make many queries. So the limitation here is that you don't, like many times you actually want to make adaptive queries to the database. Like you want to read a newspaper article every morning. You don't want to read a million newspaper articles all at once. And this kind of batching doesn't actually work for that. The other kind of batching is if you have many queries from different clients. So a server receives many queries from different clients and wants to answer them all at once. And the way you can do that is if your PIR scheme has the property that the server's work is, say, a matrix vector product, where the matrix is somehow representation of the database and the vector is the query, then you can answer many queries using a fast matrix multiplication algorithm, because then the server's work to answer many queries is like a matrix-matrix multiplication. And you can get some little speed up. I've never seen this work in practice. It's just the batch size needs to be too big. The algorithms are too slow. But at least in principle, it's possible to do this kind of batching. Yeah?
Maybe you answered this before. Can we assume there's some generic way to move semi-honest to malicious servers, or like all the results you're talking about are like for semi-honest?
Yeah, so at least traditionally in PIR, you think of the privacy property as holding against malicious servers, but correctness doesn't. All the schemes satisfy that notion.
No, so correctness, none of them like.
Correctness, none of them, as I've described.
I mean, in the computation setting, you could use signatures. But
You can always use proofs, right? Zero-knowledge proofs to do this.
Information.
No, sorry, in the computational setting.
The results of the information theory.
Yeah. Good. I don't think the picture is as clean there. There's definitely some things you can do, but I don't know that there's a generic technique that I know of. Yeah, good question.
Henry, it depends how you define privacy, right? So if you have a board, so
see about with bar about the subject.
Yeah.
Was that the same question?
Yeah, I missed it, but I think Stefano said it also depends on how you define privacy. So, for example, there have been a couple of papers recently looking at privacy where the server not only sees the client's query, but also sees a bit of information about whether the client accepted or rejected the answer. And somehow you have to be very careful about not breaking security when you want this kind of, It's like definitions get more complicated, but.
Maybe I didn't follow the thing. I mean, what Stefan was saying is side channel. Like, I mean, I know based on accepting or rejecting the privacy, but my question is about correctness.
Yeah, so maybe to say it differently, like a naive way to get correctness against malicious service would be to use signatures or some kind of signatures or Merkle trees or something like this. And a naive composition of signatures / Merkle trees / some authentication primitive with PIR doesn't provide exactly the privacy property that you would want. Yeah. Good. So Stefano has a paper on this. We have another paper. It's like there's a few people have been interested in this because in practice, the server may be able to learn whether you accept it or reject it, and so you have to. Good. So those are called malicious secure PIR or authenticated PIR schemes. OK, so the other approach is this PIR with client preprocessing, which I think the first work was this PPI paper in 2018. And the second paper, which gave sublinear server time, is from me and Dima Kogan. And the idea here is it's a PIR scheme that works in two phases. In an offline phase, the client somehow gets a hint about the database from, in the two-server setting, I'll call it the left server. So the client talks to the left server first. And then thereafter, the client can make many queries in sublinear online time by talking to the right server. And there's many kind of variants of this model. Just to keep it simple, I'm gonna state it like this. And for security, you need the servers to not collude. In particular, you need the online server to not know what the client's hint is. So if you're willing to make sort of use homomorphic encryption, you actually only need one server. There's protocols that let you, the client, fetch the hint without revealing to the online server what it's getting. Yeah?
Basically, the difference is this. I can also imagine as a two-round rather than client preprocessing. You're saying that I need to do the offline phase, and after that, based on it, do the online phase. So, but if I had these two servers, it's also like a two-round protocol.
Yeah. I think the interesting thing is that you can run the offline phase many times. Or sorry, the online phase many times. So you run the offline phase once.
If I do it in parallel, it doesn't matter.
So remember that you need to hide the answer of the offline phase.
So I think that at least the model I'm thinking of is you talk to the left server once, and you talk to the right server every time you want to make a query. And the total communication with the left server is like square root of n bits. And then you never talk to the left server ever again. So it's not just kind of a two-step PIR protocol. It's something slightly different. Yeah, so there's two ways that you can, or three ways you can implement this. One is with two servers. The second is using some kind of MPC between the client and the single server. And the other way is the client can download the whole database and act as the kind of left server. And people have looked at all three.
So this is conditional. So what assumptions do you need, like one-way functions?
Yeah, I'll come back to it. So if you, in the two-server setting, we know there's no information theoretic PIR, but in the two-server setting, you can get this kind of complexity information, something close to this information theoretically. But the construction I'm going to sketch uses a PRG in two servers. So I should say, I guess that. So the first sublinear time scheme that had sublinear online time used two servers in a PRG. And there's been a ton of work since then improving these schemes in various ways. So information theoretic security, reducing the online time, reducing the client work, reducing the bandwidth, better lower bounds, updates, all sorts of stuff people have looked at. And the bottom line is after all these improvements, the online times of these schemes, it's like 1,000x faster than linear time PIR on a reasonable sized database. So these actually do give serious performance improvements for realistic database sizes, which is very cool. The limitations are, there's like two that are annoying in practice. So one is the client now has this hint about the database contents. And the client's hint needs to change as the database changes. And very often, the database is actually changing quickly. And so the client might have to download a lot of information to update its hint. The other annoying thing is that the per client setup cost is hundreds of times more expensive than a single linear time PIR. So this approach only makes sense when you actually want to run the online phase many, many times, like 1,000 times or more. And because it also only makes sense when the database doesn't change, it sort of restricts the applications where this ends up being useful. So one direction here, Ling Ren mentioned this, is he wanted to see better single server schemes. So the single server schemes where the client, the offline and the online phases are run on the same server, they either need FHE or they have worse parameters. And so coming up with kind of an elegant way to do this would be very cool. Any questions on this so far?
What's wrong with Pushilevich-Ostrowski, like using this additively homomorphic encryption?
So additively homomorphic encryption, at least without extra work, doesn't let you run the offline phase. So you can use it. What happens if you plug in additively homomorphic encryption to generate the hint is the hint size ends up being like n to the 2/3, and the online time is like n to the 2/3 with a terrible constant. So I think we don't know.
And it's not clear how to recurse because of the offline part.
Also, like the way the hint is not just, the hint is some complicated function of the database. And so fetching this hint using PIR is not immediate. You actually need to do something more complicated. Actually, how many people have seen this CK20 PIR scheme before? Okay, so actually I have time to sketch the main idea, which I'm also hoping is useful in MVC beyond PIR, because it's a very simple idea which makes me think it should be useful in other places. So this is how to build a very high level offline-online private information retrieval, where you talk to one server once, it takes linear time for that server to answer you, and then you talk to the second server many times, and it can answer you in sublinear time. And again, this is joint work with Dima Kogan. So the idea is the client in the offline phase imagines partitioning the database into square root of n chunks, each of size square root of n. And it sends that partition up to the left server. And you can compress this using a PRG if you want. Then the left server, what it does is it computes square root of n bits, where each bit is the parity of the database bits that are indexed by each of these sets. So for the first set, the client takes the database bits indexed by this set, XORs them all together, and that's the first hint bit. It does so for all these square root of n hint bits, and then sends the hint bits back to the client. So this takes the server roughly linear time to do. The client has this hint, which it can store, if you're using a PRG, it can store it with like square root of n bits. And that's the end of the offline phase. So next, when the client wants to fetch a particular bit from the database, so say it wants to fetch bit I, what it does is it finds the set Sj that contains I, and there's going to be one of those sets because this partition covers the entire database. And then most of the time, it sends to the right server this set Sj with I removed, and I'll call that set S prime. And with small probability, it does something else and fails. But most of the time, it sends set Sj minus I. The right server does kind of the same thing. It just takes the parity of the database bits indexed by the set, returns the answer to the client. That's a single bit. And then the client XORs together the jth hint bit and the answer that the server sent. And I claim that's the ith bit of the database. The reason is because this hint bit hj is the parity of these database bits indexed by sj. And the answer is exactly the same thing except with I removed. And so when you XOR these things together, you get exactly the ith bit of the database. And moreover, the right server, to answer the client's query, only had to touch square root of n bits of the database. It didn't have to touch every bit of the database to answer this query. So that's the basic idea, which is kind of sparse subsets, taking sparse subsets of the database and then using that to get sublinear online time. And if you work through this, getting security requires you to carefully set up how this failure event works, but you can. And then the total communication is roughly square root of n bits, and the total computation in the online phase is also square root of n. So there's a bunch of things that are problematic with the basic approach. So I didn't say how the client makes multiple online queries with the same hint. You have to be more clever there. Client time and storage can blow up if you're not careful. Like, how does the client find which set to use actually requires a little bit of thought. The hint generation time can be big. People have optimized that really nicely. There's a bunch of low order terms, information theoretic security, and handling database updates elegantly. There's a bunch of ideas here that I think are extremely, extremely nice. So recommend looking at these if you're interested. Yeah?
Do something else to include I in the set every once in a while?
Yes. Yeah, exactly. So that you don't want the client set to never contain I, because then the server, of course, knows that I is in the set.
And you don't need to do this too many times.
You need to do it something like 1 over square root of n, with probability 1 over square root of n. And again, people have optimized this away so that you don't have failure, complete failure. Yeah, there's many tricks you can play. Yeah, good point.
Is there a coding abstraction of this thing? Like, if you think about type by sparse matrix, like maybe there's a better way to choose the matrix.
Yeah, so the question is there a coding abstraction? I would love to see one. I think the other thing that's weird about these offline-online schemes is that essentially all of them use the same trick. There's like this one trick that gets used in many different ways, but it would be really neat to see some other there's like no algebraic kind of construction that I know. Yeah, it would be neat to see, but I don't know. Yeah, good questions. Okay, so let me talk more briefly about the last way to circumvent this lower bound, which I think is kind of the most powerful one, which is to don't store the database in unmodified forms. Encode the database somehow so that every bit of the encoding depends on every bit of the original database, and that lets you subvert this kind of lower bound. So there's two approaches here. One is multi-server and one is single server. Both of them, I think, are really beautiful, beautiful constructions. So the multi-server construction, stuff you can get information theoretically, and I'll say a little bit more about how this works, but the bottom line is that if you have two servers, a polynomial size encoding of the database, then the per server time is something like n to the square root of n, with not quite, but close. But the downside is these encodings are big. So if you want to get like n to the 0.6 online time, the encoding size is cubic in the original database size, which even quadratic is kind of too much for any reasonably large database. The single server schemes, we only have one construction, and this is from ring LWE. This is this Lin Mook-Wicks construction from a couple of years ago, also super cool. And there with a polynomial size encoding, the per server time is actually polylog in the database size, which is sort of astounding that this is possible to me. But it's costly in absolute terms. So I'll say more about this in a second, but for like a 400 megabyte database, it's going to cost roughly like $10 billion to run the pre-computation. So it's not fully practical yet, at least with the constructions that we have. Yeah.
It's all VC money.
Yeah. For the right person, this is not expensive.
I usually make an AWS joke, but now it's...
All right, so the multi-server construction, I think, is super nice. This is the one that I'm actually optimistic in the potentially nearer term to being usable in practice. This comes from the same BIM paper I mentioned before. And the idea is just have the servers pre-compute the answer to every possible query the client could send. And if the upload is u bits, then the servers have to store like 2 to the u pre-computed answers. But I already mentioned that you can get from this derivatives trick, if you go to higher order derivatives, a PIR scheme where the upload is order log n bits and the download is something. And if you plug in that PIR scheme to this idea, you get a pre-computation, like a doubly efficient PIR scheme for multiple servers where the encoding has poly size, and the server computation is like n to this 0.6 bits reading from memory and sending back to the client. So I think it's just that. So it's very, very nice. Whenever you can make a PIR scheme with short queries, you get a pre-processing scheme. And I think the interesting question here is, can you do better than the trade-offs in this BIM paper for two-server doubly efficient PIR? I think this is implied by better two-query locally decodable codes with large alphabets, but there could be some other way to get it that uses something totally different. So that's multi-server. Yeah, so single server is also a super elegant construction. I'm just curious, how many people know this result? Oh, OK, good. So not that many, actually. So this is quite recent. I think many of us suspected that this was not possible, but it turns out you can get this from ring LWE. The way it works is you find a PIR scheme where the client's message to the server is a single ring element. Say it's a ciphertext. And the server's answer is just to apply the database polynomial to that ring element. And the basic single server PIR scheme I mentioned at the top of the talk, if you plug in ring LWE-based homomorphic encryption to that scheme, it has this structure. And I'm hiding the fact you have to be very careful about the parameters and so on. But this is the basic starting point. And then what's the server's work? The server's work is just a polynomial evaluation. So find a data structure for fast polynomial evaluation and use this data structure to speed up the server's work. And there's this Kedlaya Uman's very clever data structure for fast polynomial evaluation that applies when you set the parameters correctly. And that gives you a PIR scheme where the encoding size is like n to the 1 plus epsilon, and the per query server time is polylog in the database size. And that's the whole construction. So maybe to say it a different way, if you have a PIR scheme where the server's work is some computation, and you know some data structure for speeding up that computation, that immediately gives you pre-processing PIR scheme or doubly efficient PIR scheme. I'll just say a little bit more about the concrete efficiency. So someone actually tried to compute these numbers for this doubly efficient PIR scheme. And you can see, I mean, we're quite far from practical. In particular, like the communication per query is larger than downloading the whole database. So not there yet. So yeah, a few people mention their interesting questions. David Wu and Ling Ren both asked for a practical single server DPIR. And I'm going to define practical, just to make it concrete, as like 10 times faster than linear time PIR for an 8 GB database. And I think even if it's not practical, any different construction would also be super interesting. Yeah, I guess Lee put a paper on ePrint recently showing that you can get a slight speed up just by using fast data structures for matrix vector multiplication. But I think getting beyond that would be cool. I already mentioned practical multi-server DPIR would be extremely interesting for any constant number of servers. And then the last thing would be speeding up these client-side preprocessing schemes in the single server setting. So OK, takeaways from this section. There's many ways to get PIR with sublinear server time. These doubly efficient techniques, I think, are the holy grail. No reason to believe that we shouldn't be able to get much better schemes. So I hope that if you're interested in PIR, this is one of the questions that you think about. So I'll talk very, very briefly about some applications. I think the application I'm most excited about is basically using PIR to browse the web. So you could imagine in some future world, a company is able to ingest all the web pages on the web and make them available to clients via PIR. So you could look for whatever, like read a web page by talking to this PIR infrastructure, and no one would know, what medical condition you're Googling about. I think that would be very cool. And it's like, so Emma Dotterman and I tried to imagine what this would look like and go through the computations. And it's definitely not, I say borderline workable. It's definitely not practical today, but I don't think it's completely out of reach to imagine such a system could exist. There's 2 public deployments of PIR at large scale that I know about. Both are by Apple. Both use a ring LWE-based linear time PIR. And I'll mention them briefly. Both have pretty small databases, again, because they're using linear time PIR. So computation cost is still the bottleneck. The first is something called live caller ID lookup. So Apple wanted to make it possible for any random app to offer spam filtering as a feature. So they can have random companies offering spam filtering apps. But you don't necessarily want to give away all of your call logs to the spam filtering app. So there's some APIs now on the iPhone where they will use PIR. Your phone, when you get a call, will use PIR to check the incoming phone number against a spam database without revealing who's calling you. So that's one. The other is this feature called enhanced visual search, where in the background, your iPhone is constantly attaching tags to photos, like this is an apple, this is a tree, this is a bus, et cetera. And the way that works is that your phone takes some kind of visual hash of the photo and then searches this visual hash in a database of hashes that Apple maintains. And to privately make queries, it uses PIR-like stuff. It actually is private nearest neighbor search, but basically the same. And in the implementation they're using now, they actually leak some bits of information about the hash to the server to speed up this PIR computation. So again, the linear computation time is the barrier. I guess the last thing I wanted to mention before I wrap up is that when I talk to companies about using PIR, the thing that always comes up, which might not be obvious to cryptographers or to me beforehand, is this competition is actually not using PIR. It's using an anonymizing proxy to get privacy. So what does that mean? It means if Apple or Alice is querying some database, instead of running a PIR protocol with a database, Alice will just encrypt the message to the database, send it through some proxy, which could be Tor or some other company, to Apple. Then Apple can decrypt the message and sees, oh yeah, someone wants record I of the database, but I don't know who it is. And then they return an encrypted message back. And the idea is like, well, maybe it's OK if Apple learns the index I that Alex is after, if Apple doesn't know who Alice is. So somehow separating the identity of the person making the query from the contents of the query. This definitely doesn't provide PAR type semantic security because the server learns exactly what the client's looking for. But maybe this is actually OK. There's people in industry seem to think this is OK. And I would love to see kind of a more principled understanding of when this is OK and when it's not. Yeah.
The other computation is ORAM plus enclaves, right?
True. Yeah. ORAM plus enclaves. Yes. So I hear about this less than I used to, maybe. But there's definitely, I think, Signal is using ORAM plus enclaves for some things, which is another way to implement much more like there you do get the PIR type of security under the right assumptions about enclaves and so on. OK, so just to wrap up, I think there's been a ton of advances in PIR in the last 30 years. So exponential improvements in communication, at least in the two-server setting, many different sublinear time approaches, and some applications. So these things are really running in your iPhone, which I think is extremely cool. I think linear time PIR is good enough in some cases, but I think these doubly efficient PIR schemes are really the exciting thing to see. I really hope someone comes up with new constructions in the future. So I'll finish there. Thanks so much.
Additional questions for Henry?
Oh, sorry.
Yeah, go ahead.
Is there this is a naive question. Is there a connection between PSI and PIR that
You can definitely
seem stronger?
Yeah. I mean, you can definitely build one from the other. I think there's loss in the parameters in each direction. But I think I'm not a PSI expert, but I feel like some of the PSI schemes I've seen are essentially doing PIR, especially when the set sizes are very unbalanced.
PIR just has a one-sided privacy. If I'm not,
yeah, so
it's like a symmetric view.
Yeah, so you can upgrade PIR with like an oblivious PRF to get two-sided privacy, and that's essentially I think how you do PSI. Right? Yeah, good point. Yeah.
Yeah. So the first approach that you mentioned can be applicable also in the next two approaches, the weakening correctness, and if you know the distribution, that can reduce the pre-computation size for hints as well as reduce the database size.
Yeah. This is a good point. So you can actually apply many of these strategies at the same time. And one also thing I should have mentioned that I think is an interesting question. For these client preprocessing PIRs, can you speed up the hint generation time by encoding the database? So I think mixing the second two strategies would also be interesting, and I haven't seen anyone successfully do that yet. Yeah, great. Any other questions? Awesome. All right, thanks so much.
Thanks, Henry, again.